Around 1912, Alfred Wegener proposed the theory of continental drift. According to this theory, millions of years ago, the continents were joined together into one supercontinent called Pangaea. Over time, the continents have been gradually moving across the Earth's surface. Although Wegener had made many observations and gathered a lot of evidence supporting his theory, he could not provide a clear explanation as to how the continents moved. Scientists of his time rejected his theory, and it would be several decades before they would start thinking about it seriously. In the 1950s, Marie Tharp, a cartographer, that's a map maker, and Bruce Heezen were working together to map the ocean floor. Marie discovered a V-shaped structure in the mid-Atlantic ridge. She believed that it might be a rift valley, formed by two parts of the ocean floor that were being pulled apart. Others didn't believe her, and they dismissed her ideas as girl talk. But soon after, other scientists who were mapping earthquake data found that earthquakes were happening along the Rift Valley, and this suggested that the ocean floor might indeed be pulling apart, and that continents might indeed be moving. Tharp and Heezen found similar ridges in other parts of Earth's oceans, suggesting that the rifts were a set of breaks in the Earth's crust. Scientists started to take the idea of continental drift more seriously, and other discoveries were made that helped develop the theory of plate tectonics. In the 1960s, Harry Hess noticed that the seafloor gets older the farther you get from the mid-ocean ridge. He concluded that new seafloor was continually being created at these ridges, and as new crust formed, it was pushing these large pieces of crust, which we know to be tectonic plates, apart. Hess called this process seafloor spreading. Here's how seafloor spreading works. Hot rock from deep inside the Earth rises, and as it gets toward the top, some of it melts and becomes magma. The magma pushes through cracks in the seafloor, and it creates new crust where the plates come together. As the new floor is created, the older seafloor is pushed apart, pushed away from the mid-ocean rift. One way we have confirmed that this is happening is through magnetic polarity reversal data. The Earth's magnetic pole shifts every few million years. As new crust is formed at mid-ocean ridges, iron-rich crystals in the forming rock align themselves to point towards the Earth's magnetic poles. They get frozen in the rocks as the rock cools. Depending on which direction the magnetic north and south poles are pointing, the forming rock will be magnetized in one direction or the other. Scientists have noticed that the seafloor on either side of the Atlantic ridge is magnetized in long strips that are symmetrical on both sides of the ridge. The strips alternate in the direction of their magnetic polarity, which depends on where the Earth's north and south pole were when the stripes were formed. The rock in matching stripes on each side was formed at the same time. Then it was pushed outward through seafloor spreading as new crust was made. As new seafloor is made, old seafloor is recycled, and this would make sense because our Earth is not just getting larger and larger and larger. Seafloor recycling occurs at deep ocean trenches. The famous Mariana Trench is one of these. As ocean floor ages, it becomes denser and denser, and eventually it will sink under newer floor that is less dense or under continental crust. As the old floor sinks, it melts and it is recycled into the Earth's mantle. Seafloor spreading and the recycling of trenches is what's responsible for the movement of the continents. Well, there's a little more to it, but we'll get to that in a future video.